If no, then let's go ahead. Why bandgap materials? I uploaded some paper. They are pretty very what is called important paper, right? Many people refers to this. The first two paper is about gallium nitride. The last paper is about the general ultra wide bandgap device. Okay, just a qualitative view, right? We have all the basics on this material, etc. Let's look at what type of device we have. You know the transistor very well. You have source and drain in the logic. But how about power device? Power devices are actually very diverse. There are many things, a lot of things for you to explore. Compare with transistor. Transistor is so, logic is so boring. Yeah, now you have FinFET or whatever, but still just source, channel, source, right? Power device, the first thing is the Schottky diode. Silicon carbide device is very similar to silicon device. For example, they have the Schockkty diode. What is the Schockkty diode? You know, right? Just from it is just a diode. If you measure the current, it goes up like this. This is a Schockkty diode. And this is the symbol. Why we have an RD? Because we have a very large drift region. This is the region when you are on, right? For a Schottky transistor, if you do plus minus here, then you have current. If you do minus plus here, you don't have current, right? It turns off. So when you have a current going from here to here, then you actually have a big resistor we call drift region. And this is going to increase your resistance and increase your power loss. But why we want to do that? You must say, hey, why want to make this so thick? Any idea why I want to make this thick? Anyone? Remember, when we're talking about power device, it's two things the most important.
Reduce the capacitance.
Say again?
You make it thicker to reduce the capacitance.
You want to reduce the capacitance?
You said what happens when you reduce the thickness, right?
My point is, yeah, or why I want to have a thick drift region. When I have a drift region, then I'm going to have a lot of resistance, right? So why I don't reduce it? So when I reduce it, what happened? Can you say again?
The breakdown voltage would decrease.
The breakdown voltage will decrease. In our class, it's always on current, on resistance versus breakdown. Just now you mentioned about capacitance is also important. That's related to loss also, right? So capacitance is indeed important. But here we only talk about here we just say that. Why I want to make it so thick? Because if I make it thin, this electric field is when you apply negative and positive. Reverse bias. You want this to be thick so you can sustain a very large potential before it breaks down, right? I will go to this later when we derive the Ballinger figures of merit. Okay, so you see a trade-off. If I can make this drift region very long, the breakdown voltage will be very high. But then it is very resistive. I lose a lot of energy. Is that okay? Another type of device called junction, barrier, Schottky, diode. Very long name. If you compare this one against this one, what's the difference? Do you see any difference between this one and this one?
The contact.
The contact here, right? I have an extra P. So you tell me, what is this? This is a Schottky diode, right? This is Schottky. And what is this? This is also a diode. What do you call this diode?
PN junction.
PN diode.
Pin diode.
Yeah. So by using PN diode and Schottky together, it has some benefit. Okay. So why? First of all, Schottky has a low VBI. This is the point you pick up. If you want to turn it on, like when you really turn it on even at 0.00 volt, right? Don't ask me to wait for 0.8 volts in order to turn it on. Schottky diode has this good characteristic. It turns on very early, right? For example, it can be, let's say 1 volt, just an example. For PN diode, it has a high VBI, right? For silicon carbide, it go to 3 volts because the band gap is free, right? So I really don't have time to go into all those device physics because we too many devices. But I hope that if you go back, just draw the band diagram, you see the Schottky contact, and Schottky diode and PN diode has this characteristic. Then why put them together? While Schottky, you have low VBI that is good, but it also have low breakdown voltage. PN diode, it usually has high breakdown voltage. So we combine them together. When it is in the reverse bias, right, I would just say it, you will have a depletion layer to the right. You deplete everything. So you just like blocking by the high breakdown voltage of the PN junction. In forward bias, before this PN diode is turned on, Schottky is already turned on. So you have a low VBI. So this one compared to this one, it enjoy the high, right? So JBS, it enjoy the high BV of PN diode and low VBI of the Schottky contact, Schottky diode. Okay, a lot of physics there, but I just want you to be aware of that, right? In the future, when you see this, come back to here, look at the slides, and here I summarize why they want to do that. But for physics, I'm not going to explain, right? You can Google or look into the Wikipedia. But you know that sometimes we use Schottky diode, but very often in the products, they use junction barrier Schottky diode. Okay, they are the same, except I have an extra PN junction in this JBS. Any questions?
Professor, so drift region is basically just to control the breakdown voltage.
Yeah, control the breakdown voltage at the same time with the resistance, low resistance, right?
So, like more the drift region, more higher is the breakdown voltage.
Yes. If the drift region is thicker, the breakdown voltage will be larger. I'm going to, because of this depletion field, but you have higher resistance.
Okay. Okay, Professor, thank you.
Okay. Any other questions? What else do we have? A lot of stuff, right? You don't understand. I mean, you will feel too much, but I just need to tell you the terms. What else are out there, right? Junction FET, JFET. So what does it do? Let's look at this one. Usually we know source, gate, drain, right? That's what we learned in the logic. Let's look at this. This is also source, gate, drain. But now my source is N-type, N plus, okay? In our transistor, what will be the doping of the substrate of the body? Is it N or P? In transistor, in our logic, what we have learned, right? For NMOS, the body is what type?
P-type.
P-type. Do you see here? The green one is N. So there's no PN junction. So it is N-type. Then how are we going to turn it off, right? Because now this is just a simple resistor. And this is something called JFET, junction FET. JFET. This is an old device, even in the past, right, in silicon. But by doing this, what they do is that then you don't have the PN junction, but you don't have the PN junction along this line, but you actually make the gate as a PN junction, right? This is a PN junction. When you apply a negative bias, what will happen to the PN junction? If I apply a negative gate bias, what happened to the PN junction?
Reverse bias.
Reverse bias. So reverse bias means what? You are going to have
No current
depletion.
or depletion.
Yeah, right. Depletion increase when VG becomes negative, more negative. Okay, and that's how you control the device. Apply a negative bias, it depletes all the electron inside, then it is no longer conductive. Is that okay? Right, so this is one type of device you see very often in the power electronics. Okay. Another is on the right. Let's look at this. It is still just a regular MOSFET, but it is very different from what we see. Hey, it has source here and source here. Where is the drain? It's at the bottom. The whole wafer is one transistor. Maybe not whole wafer. Whole die is one transistor. And where is the channel? Look at the P well. Here is the channel. This is the channel. So how does the current flow? When the channel is formed, the current flow from positive terminal go up, N, no problem. It's just some resistance N. Well, then come to here, when it is inverted, I can go through. Do you see that? So basically, it's still a MOSFET. But I rely on this very thick layer of the drain. Why do we want to do that? Do you know why? Why I don't just do a regular transistor?
Again, if we compare with the previous slide of our breakdown voltage.
For breakdown. Because remember, this can be 100 micron. We are using the wafer or even 1 millimeter, right? So this is the part that you turn it off. But the problem is you make it so thick, when it is on, you have to travel 100 micron. It's very resistive. So there is an optimization issue between them. Okay, this type of device is called DMOS. Double, or sometimes they call it DDMOS, but you call it DMOS is okay. Double diffuse, MOS, and it is a vertical device. We call it vertical. That's when you see people say this is a vertical power device. It means it flows from the top of the wafer to the bottom of the wafer. Let's say again, what is a wafer? This is the wafer. Do not think this is thin. This is talking about 500 micron. 0.5 millimeter. Think about that. We're talking about integrated circuit. Now you say that you can use your eye to see the drift region. 0.5 millimeter. Okay. Double diffuse is related to its fabrication process. Again, I don't want to say that, explain. Basically, how do you form these two well? Is through something called two implant and then diffusion. That's why it's called double diffuse, right? But this is, I think, probably many of you the first time to see what is a vertical device. Okay. On the right, this is simple, BJT. But maybe you don't know because some of you might not learn this nowadays. We sometimes skip the BJT. Bipolar, junction, transistor. Okay, BJT. So I don't want to spend too much time. You have base, emitter, and collector. You see this base is like this. Again, I have very thick drift region, vertical BJT. This is a vertical BJT to sustain the high electric field. If you have not heard about BJT before, that is fine. It's just like a MOSFET. The base is nothing but just the channel. But instead of gate oxide, you connect to the channel directly. So for this one, if you don't have other defects, your subthreshold slope is 60 millivolt per decade. Remember, we lose some subthreshold slope because of the COS, because of the potential divider effect. But you cannot get that because it has its own long ideality. Okay. Any questions? Right. Again, because of time, I can only give you this superficial thought, right? Gallium oxide, I just want you to know that gallium oxide comes with different form also. Just now we talk about silicon carbide with different poly type. We have different crystal. Silicon carbide also have cubic and hexagonal. That's why we have 3C, right? But we usually we do 4H. Gallium oxide also have different poly type, alpha, beta, gamma, delta, epsilon. But only the beta one is stable. So that's why usually when you see beta gallium oxide, we talk about beta gallium oxide. Lattice crystal is monoclinic, we mentioned before already, and these are the parameter. So I'm not going to go over it, but I do want you to really know that why they are so important nowadays, because they are cheap to grow a large gallium oxide wafer. Okay, this is what is driving it. Right, but I have, but in some conference, right, the gallium nitride, silicon carbide guy doesn't like gallium oxide, right? All the paper they would reject or whatever. But this is ultra wide bandgap. Okay. For gallium oxide, the most important thing is here, and let me mention. It doesn't have p-type doping. Then what can we do? Now we just learned that. Remember the JFET in silicon carbide, we just dope this part as N, right? We can do the same thing. So this is one of the gallium oxide transistor. Now, what is the dopant? Silicon is the N-type dopant in gallium oxide. Okay, so when you see silicon and give you N+. So what we do is we dope the source and drain. This is source, this is drain with N+. So this is N+. And then here we use tin, or you can use silicon also. Lightly doped becomes N. And this forms the so-called, looks like a JFET, but we add an insulator here. But it's the same. The problem is just that when you apply zero gate bias, when VG equal to 0, current is larger than 0. Okay. And we call this long moly on. For transistor, when we put zero bias on the gate, usually it's off. But this one has a VTH smaller than 0. So let's look at this graph. You see that this is IDVG, IDVD, and you see that at 0 by gate voltage, this is a gate voltage, it gives you 0. The threshold voltage is at negative, maybe not negative. Based on this, it is about -10. Okay, like this is a power device. You feel, wow, that is ridiculous. We are going back to 1950s while you use -10 volt to turn off a transistor, right? But This is power device. It is okay. They have their use, right? We are not looking for 0.2 volts, 0.5 volts, right? VTH is around this value, -10. Okay. And another thing is this. Can someone explain to me what is this? Why when I increase the voltage, drain voltage for the same gate bias, why when I increase the drain voltage, the current is smaller? Is it possible?
Professor, that is gate voltage.
Due to what?
It is the +4 volt is the gate voltage.
Yeah. The +4 volt is the gate voltage. Yes. So for the same gate voltage, why when I increase the drain voltage, I got smaller current? What can be the reason?
Higher resistance?
Because of resistance. Why? So I have a resistance, right? If I have resistance, I should be low at the beginning already. Why when I increase the drain voltage, the resistance is larger?
The heating.
The heating, very good. When you increase the drain voltage, right? V times I increase, so heating increase. So as a result, your mobility decrease. And that's what we call self-heating. And I think I mentioned this in SOI already. SOI has this problem also, right? And that is because you have very bad thermal conductivity. All the heat generator cannot be carried out. So it heat up the crystal, right? So this is one problem we need to solve for gallium oxide. Okay, so that's all I want to introduce about gallium oxide. Any questions so far? Right, so this is just to give you a feeling, right? I don't require you to memorize the device, but probably if I draw it in the exam, you kind of should be able to hand-wavingly tell me how it works, right? Have some idea, at least some reasonable idea. Now let's go to more math now, right? Last time we talked about Johnson figures of merit. It is about the power device for RF. Right. If you remember, I say that it's a trade-off between two things. Do you remember what is the trade-off that we care about for the power device in RF?
Frequency and breakdown voltage.
Frequency versus breakdown, very good, right? So why we care about this? Just always think about the base station, okay? Your cell phone base station. They need to supply very high power to you. So they need to sustain high voltage because you need to apply high voltage in order to get high power at off state, okay? And of course, for cell phone, talking about 5G, 6G, maybe even 7G in the future, if there is, then you need frequency, right? That is